So today we have the pleasure of having Adam Freeze give us a talk. So Adam was a postdoc at Argonne and at the University of Seattle before coming here with us, and he's an expert on mechanical form factors and light front dynamics. And now he's with not us technically, but the CNF. And today he's going to tell us about how stressful deuterons are.
Thank you for the kind introduction. So this is work that I'm doing in collaboration with Alan Sosa and Wim Kosen at the Florida International University. So this is very exciting work that we almost have a paper finished for, and I'm looking forward to telling you all about. Before actually getting into the subject matter itself, I kind of want to justify why I'm looking at stresses in the A big part of the motivation is that stresses in the proton are already a really hot topic in the field. Not only has JLab gotten 2 Nature papers out of the measurements of proton pressure, quark and gluon contributions to the proton pressure respectively, but there have even been popular science articles written about these measurements and about pressure in the proton. So it's a pretty hot topic that is moving a little bit beyond just our little academic field. It's gaining some popular interest. At the same time, there's also some controversy about the validity of the mechanical interpretation. So we have both popular articles, controversies. Makes it a very exciting topic. Looking at the mechanical properties, not just of the proton, but the deuteron allows for elaboration on all of this and could potentially touch on the controversies too. The deuteron is a spin object, so its stress tensor is actually a lot richer than the stress tensor of spin 0 or spin half objects. There are more kinds of stress. There are things that are no longer radial. It gets very interesting. Secondly, we can use old-fashioned traditional non-relativistic quantum mechanics to describe the deuteron to pretty reasonable accuracy. This makes the calculations more straightforward, and it makes the interpretations more straightforward too. Finally, we can talk about the connection of these mechanical properties to the nuclear force. And this kind of goes 2 ways. The nuclear force is fairly well understood, so we can use our understanding of the nuclear force to guide the way that we interpret these mechanical properties. At the same time, there are things we don't know about the nuclear force, and perhaps looking at the stress tensor can give us a new perspective and greater understanding of the nuclear force. So that's why we're looking at stresses in the deuteron. So this seminar is going to be divided into 3 sections. I'm going to review some basics of what the energy momentum tensor and what stresses are. Then I'm going to show results for the form factors of the energy momentum tensor. Not just our results, but comparing to previous results where they exist. And then I'm going to talk about spatial distributions of stress, as well as some other properties that we get for free by looking at the energy momentum tensor, like mass distributions. This is actually the coolest part. The plots look pretty cool in my opinion. So to start with, the energy momentum tensor. So the energy momentum tensor is a rank 2 Lorentz covariant tensor. You can think of it as being a 4x4 matrix that consists of an energy density, 3 momentum densities, 3 energy fluxes, and a 9x9 submatrix that we call the stress tensor. It is a conserved quantity associated with symmetry of the QCD action under spatial translations, either global through Noether's first theorem or local through Noether's second theorem. The benefit to using the second theorem with local space-time translations, by which I mean you change the field configuration by moving where it is at each space-time point by a different amount, is that the energy momentum tensor you get by this method is automatically gauge invariant already. So you don't need to do a Bell-Infante improvement step. In fact, looking at this from the perspective of Noether's second theorem also helps justify the interpretation of this 3x3 submatrix as a stress tensor. The rationale behind this is that the stress tensor is something that is associated with the energy of deforming a continuous object. So you imagine your hadron as sort of a continuous object by coarse graining over all the quarks and gluons in it. And you want to talk about how much work do you need to do to deform it in a particular way. Say, translate all the quark and gluon fields by different amounts. Squeeze it, pull it, shear it, whatever. Then by the way that the action changes, you can infer that the effective potential, because you are kind of considering internal kinetic motion of quarks and gluons as being sort of a potential energy here, just as you might do with vibrations of atoms in a solid you're compressing. You get something that's a contraction between what you're calling the stress tensor and your strain tensor. And if you're using an asymmetric energy momentum tensor, a torsion tensor as well. So you can kind of think of these hypothetical deformations as being a virtual pressure gauge. In addition to interpreting the submatrix as a stress tensor, there's also a valid interpretation of it as a momentum flux density or a momentum current density. The justification comes from something as fundamental as the continuity equation, which follows from local conservation of the energy momentum tensor. You can write it in an integral form as such, and this tells you that the momentum in a region of space changes because momentum is flowing out of that region or through the region or into the region through its boundary. Now, stresses or momentum flux densities can come from a variety of sources. The two main ones are either that particles can flow into or out of the region, carrying momentum with them, or a force can be exerted across the boundary without particles moving through it. Both of these can impart a change in momentum, and both of them are momentum flux densities. Both of them also have a valid interpretation as stresses, especially if you're coarse graining over the particle degrees of freedom. So I would say that kinetic pressure due to motion, is a valid pressure. It's the microscopic origin of gas and fluid pressure. We feel gas pressure right now because we're being pelted by nitrogen and oxygen molecules from all directions. And photon flux, the movement of photons, is the origin of radiation pressure, which is also really important for, say, solar sails guiding some of our satellites. Now, what does the sign of this stress mean? The sign of it has to do with whether the stress or the pressure is compressive, in which case you're pushing in on something, or tensile, in which case you're pulling on it. These turtles and these monkeys, I think, are pretty nice illustrations of the difference between positive compressive pressure and negative tensile pressure. An interesting thing here, too, is that the sign doesn't necessarily tell you about whether the force that's responsible for the tension or compression is attractive or repulsive. Here you have some turtles experiencing compression due to gravity, which is an attractive force. There's more compression at the bottom, more positive pressure. And with these monkeys, they feel tension because they're being pulled on. But again, it's under gravity. There's more tension at the top because the top monkey is carrying more monkeys. So more negative stress. The stress is more positive, smaller in magnitude at the bottom. And interestingly, if you were to take the gradient of the stress tensor in both cases, you'd get the gravitational force density. So the force is actually related to the divergence of the stress tensor rather than the stress tensor itself, the net force on any particular component of your system. This is known as the Cauchy momentum equation. Some engineering and continuum mechanics texts call it Cauchy's first law of motion, but Cauchy momentum equation is more common, a more common jargon term. Basically, if you have a static system, the net force on it by Newton's first law has to be zero. So you have a combination of external forces, say gravity acting on this monkey, and then forces from the monkeys above and below it. These forces have to balance, and that tells you that the external force can be inferred from the forces exerted by adjacent cells of your system. This is a classical equation, to be sure, but it also works for expectation values of the force density and the stress tensor in quantum systems, something that has actually been talked about as far back as the early days of quantum mechanics. Schrodinger wrote about it in 1927. And there's been something of a renaissance of talking about stress in quantum systems starting in the 80s in the field of condensed matter physics. More recently, Maxim Polyakov, one of the, what's the term I'm looking for? Paragon, is that the right word? Well, a person who basically brought these stress concepts to hadron physics, pointed out just a few years ago that we can also use this equation for hadrons to map out the force felt by subcomponents of the hadron. Just last year, I put out a paper showing that if you look at the hydrogen atom from the perspective of the Cauchy momentum equation, you can infer the Coulomb force law from the stress tensor. So if we didn't already know that you had an inverse square law for electrostatic attraction, you could figure it out by looking at the stress tensor of the hydrogen atom. It would be very exciting to do something analogous for hadrons and perhaps get the average QCD force felt by quarks in the proton. So with that basic review of the stress tensor out of the way, I'll talk about form factors associated with it. You basically take your energy momentum tensor operator and sandwich it between momentum kets. You write out the most possible general Lorentz covariant tensor structure you can. That's also compatible with the quantum numbers of the operator, so you have parity and time reversal and variance too. And you write out the a priori unknown Lorentz invariant functions of the momentum transfer, and they're often called gravitational form factors. They're called that because the energy momentum tensor is the source of gravitation in general relativity. I'm going to be a little bit more neutral and just call them EMT form factors throughout the talk, but you should know that gravitational form factor is a very commonly used jargon term. And it does confuse a little people a little bit, but it is technically accurate because this stuff is the source of gravitation. So this is the general form for a spin zero hadron. Yes.
Are you no longer using mechanical form factors?
Yes, I'm no longer using mechanical form factors. The rationale behind this is that EMT form factor is already accepted terminology in the field, and I feel like it would be better to just adapt a term other people are using instead of trying to push people to use something new I came up with. It makes communication easier to use accepted jargon, I think. And EMT form factor doesn't necessarily imply that you're doing gravitational physics either, so I feel like it avoids being misleading. So this is for a spin zero target, you have 3 such EMT form factors. For a spin 1/2 target, such as the proton, you introduce potentially 2 more form factors. These new structures are related to angular momentum. You can kind of think of them as being dipole form factors and the spin zero form factors as being monopole form factors. One of these only appears if you have an asymmetric energy momentum tensor. So if you're using the symmetric one, you only get 1 new form factor. And if you want to look at a non-relativistic system, you can either do a non-relativistic reduction of this expression, or you can look at the most general possible structure you get from Galilei symmetry, the symmetry group of non-relativistic mechanics. And you get something that basically looks very similar. For spin 1, you get yet more structures. You now have 11, 9 if you discount 2 of them from the antisymmetric part. So that's a lot of terms. So I'm going to step through them to try to give a systematic account as to what all this stuff is. First, you have 3 form factors that also appear for spin zero targets. These are kind of unpolarized or monopole form factors. If you were to take an unpolarized ensemble of deuterons, these are the only 3 form factors that would survive. They're the same A, D, and C bar that appear in a spin zero target. So they're already known in a sense. Next, if you have a vector polarized ensemble of deuterons, then you only have 2 form factors that contribute. And these are the same J and S form factors that appear in spin 1/2 systems. So these are not new either. What you have are 6 new form factors associated with the quadrupole structure of the deuteron, and that survive when you take a tensor polarized ensemble of deuterons. You can tell they're related to quadrupole structure by the appearance of this irreducible rank 2 harmonic tensor and this quadrupole tensor, which multiplies each of these structures. So you get 6 new structures that describe the quadrupole structure of the Deuteron stress tensor. So that's quite a lot. Another way to try to break this down and systematically understand the individual terms are, you have something that are kind of like the A form factor that appears in spin 0, in the spin 0 breakdown, one unpolarized, one tensor polarized. You have 2 J or S-like form factors, again, the same ones that appear for spin 1/2 targets. They're related to various sorts of angular momentum properties. You have 3 D-like form factors. These are similar to the D term in the proton or the pion. One of them associated with monopole structure, 2 of them with quadrupole structure. And you have 4 C-bar-like form factors. And these are actually going to be related to forces through the Cauchy momentum equation. There are a few sum rules that are obeyed by a subset of these form factors. For instance, if you take the unpolarized A-like form factor, evaluated at 0 momentum transfer, and sum over the contributions from all constituents, you get 1. That's just a momentum sum. If you do a similar sum for the J form factor, you get 1. This is a spin 1 version of G's angular momentum sum rule. You get 1 instead of 1/2 because it's spin 1 particle. And you have 4 sum rules from local momentum conservation, where instead of evaluating just at 0 momentum transfer, evaluate at any momentum transfer the sum over all constituents of the 4 C-bar-like form factors, and they should all vanish. For this reason, a lot of people don't really consider the C-bar-like form factors. They vanish when you take account of the whole system, but it's violated for open subsystems. And that actually has interesting implications. If you look at an open subsystem and you evaluate these, get something that's non-zero, and take the gradient of your stress tensor, it gives you a force distribution on that subsystem. Yes?
So how did you categorize the C-like, C-bar-like, D-like form factors? What was the, like from the protons energy momentum tensor? Like how did you generalize those? Like C-bar-like? Because unsymmetricity is, related to the spin. Interesting spin. Here you have C-bar. So I was.
So the question was about the motivation for why I categorize them as being like certain ones. So for the A-like ones, the motivation comes from the presence of this factor Pi, Pj. So if, for instance, you were to evaluate this in the bright frame, this term would drop out. This term is related to just momentum densities. And in a few slides, I will get to that these 2 things exactly contribute to the mass density. The J and S form factors, they have 1 factor of P. So they do end up contributing to the spin densities, to the energy, mass flux density and the momentum density. The D and the C bar both contribute to the internal stress tensor or the stress tensor in the bright frame. And I sort them into D-like or C bar-like, depending on whether the divergence is 0 or not. So the 0 divergence ones are the D-like ones, and then the ones that have a non-zero divergence are the C bar-like ones. Yeah. So there are several calculations that exist. There are a small number of papers that calculate only 1 or 2 form factors, but there are 3 existing papers that calculate 6 of the 11 form factors. They get 6 of them because they look at the symmetric energy momentum tensor and they disregard the non-conserved form factors. So you get 6 remaining when you impose those constraints. There's one by me and Wim. There's one by Fangcheng He and Ismail Zahed. Another by Yulia Penteleva and collaborators, and then there's the work I'm telling you about today by me, Wim, and Alan. For our work, the way that we go about the calculation, we're actually only doing it partial calculation. The stress tensor of a multi-body system in general depends not just on the stress carried by the constituents, but also the stress in the interaction itself. So if the proton and neutron in the deuteron are bound by pion exchange, the pions themselves and the pion-nucleon vertex will carry stresses. You can consider these to be interaction or two-body currents. We do not account for this in our calculation. We are only accounting for the one-body currents, so we are effectively doing an impulse approximation. We evaluate the stress tensor by using a two-body completeness relation. So we insert, say, the one-body operator for stress carried by the proton between momentum kets. We expand the momentum kets as a sum over all possible states the proton and neutron can be in, and we get an expression that looks like this, an integral with the deuteron's internal wave function. In the nucleon stress tensor, we use the non-relativistic breakdown of the energy momentum tensor in terms of form factors, and we can use realistic form factors that come from lattice or from holography or meson dominance models. We've considered all three actually, and the results look pretty similar. For the 6 conserved form factors, these are plots of what our results look like compared to others. So to go a little bit more into depth on, say, the top row, we have this AU form factor. It goes to 1 at 0 momentum transfer from the momentum sum rule. The J of 0 goes to 1 as well because of the spin 1 version of G's spin sum rule. And then this AT actually has a interesting forward limit too. When you evaluate it at 0 momentum transfer, it's proportional to the quadrupole moment of the deuteron, hence why it's so big. Now, the first thing you might notice is that these results seem to disagree, but the results in a certain sense actually agree with each other. The thing is that the different groups use different deuteron wave functions. Wim, Allen, and I use the AV18 wave function. Fangcheng He and Ismail Zahed use the Reed soft core potential, which actually has a bigger quadrupole moment, hence why it's up here. And Yulia Panteleva and all, they do a chiral effective field theory calculation, but they effectively get a smaller quadrupole moment. So in spirit, these all agree. The discrepancy is just due to difference of quadrupole moments. Now, the D-like form factors, there's a little bit less agreement. The DUs all agree. This is partly due to design. He and Zahed use a holographic D form factor for the nucleon, and we use the same thing to make sure. There's a question online? No? Okay. And then with the chiral effective calculation of Panteleva et al., they fix one of the low energy constants to agree with He and Zahed. So the DUs all basically agree by design. The DT1s, things look a little funny. Just like with AT, we and Panteleva's group agree in spirit. The discrepancy is just due to the use of different quadrupole moments. The earlier calculation Wim and I did appears to track with our new calculation at larger momentum transfer, and then divergence. We are not entirely sure why that happens. It might be a mix of numerical instability in the old code, but also we effectively did an impulse approximation calculation in our older thing, but didn't account for non-conserved form factors. So there might be contamination from non-conserved form factors here. As for He and Zahed, they perform a substitution in their nucleon momentum of this form so that after the substitution, this is now orthogonal to the momentum transfer. They do this in order to force local momentum conservation to be observed, even in the impulse approximation. But because of this over delta squared their DT1 blows up. That's the reason for that discrepancy. As for DT2, they all disagree. DT2 seems to be extremely sensitive to minor differences in dynamics. It's basically defined to be the leftover structure after you sorted everything into structures that you had a good physical interpretation for. There's no forward limit that's constrained by Deuteron properties. And actually, if you read the papers by Panteleva et al. And Hands Ahead, these things receive massive corrections from next deleting order or exchange currents. So basically, these are very sensitive to minor differences in dynamics. So perhaps if you actually want to understand internal structure of the Deuteron in a way that distinguishes between all the wave functions and models out there, DT2 might be the thing you want to empirically measure. We have these C-bar-like form factors here, 3 of them from the symmetric part of it. We've calculated these for the first time. People previously discounted them because they vanish when you sum over all contributions, but in the impulse approximation by itself, they don't vanish. And we find that they're very sensitive both to the wave function you use, because this quantifies the force in nucleons. So if you have a different nuclear force, you'll get a different result. Differences between the orange and blue curves. But this also incorporates the finite nucleon size. Basically, it's smeared out over the entire nucleon, and as such is also sensitive to the nucleon form factors. These solid curves use the same dipole-like form factors that we borrowed from Hands Ahead, and these dashed lines use point-like form factors. So there's sensitivity there. Lastly, there are the form factors appearing in the antisymmetric part of the asymmetric energy momentum tensor. There's this capital S form factor, which is related to the spin distribution. Basically, the only difference between point nucleons and composite nucleons is you get multiplied by the SN form factor, and S bar the same. Only difference is multiplication by the SN form factor. So with the form factors in hand, we can now look at spatial densities. Need to see how I'm doing on time. Oh.
What is the C-bar-like form factors are smaller in magnitude compared to, it's nearly 0, no? Is it model dependent or?
It is, well, it's model dependent in the sense it depends on the particular wave function. That's actually a good question, and I don't have a good conceptual answer prepared offhand. I did notice in my hydrogen atom calculation that the C-bar form factor was also really small compared to the D form factor. However, it's the only thing that survives when you take divergence of the stress tensor. One possibility is that the D form factor is related to forces that balance out, that cancel out. So it might just be that most of the pressure that's felt by a subcomponent of your hadron is the stuff that cancels out. And only a very small amount is left over to give you your net force.
Yeah. And also, is it possible to look at the quark and the gluon separately and see whether
it is possible? We did not do this in our calculation, but we actually have the code in place and we could easily do it. One of the things we found as well is that all of our formulas for the form factors depend on C bar n. We are summing over quarks and gluons, so we set the C bar n to 0, but we've written the code so that you can replace C bar n with the quark part or the gluon part and get a result. I didn't say this in our slides, but we're going to release the code along with the paper, and the code will be open source. But that is a thing that we should look at, actually. That's a good point. Maybe I should add it as a bullet to the future directions on my last slide. All right, so next is the spatial densities. So something that is very unambiguously defined is you can take the expectation value of any quantum operator, including a local quantum operator like the stress tensor, for an actual physically realistic state that's actually near Hilbert space. And what you'll get is a spatial distribution. The spatial distribution depends not just on the internal structure of your system, but also on the wave packet it happens to be prepared in, how fast it's moving, how spread it out over space it is, and so on. You can see dependent on the dependence on the Deuteron wave packet. So it's smeared out by the Deuteron's actual momentum and velocity. So you need to do a bit more effort if you want to try to get internal densities instead of stuff that depends on the wave packet. And I'm going to follow some of the formalism worked out by Yang Li and collaborators, and as well as me and Jerry. So one of the really nice things about non-relativistic quantum mechanics that also extends to the light front formulation of the relativistic theory, but I'm doing non-relativistic, so I don't have to worry about light front and all that, is the Galilei symmetry and the absoluteness, the absoluteness of the simultaneity of time allows you to break down the expectation value in a fairly clean way like this. So your stress of a moving system in general will not just depend on internal stresses, but you can have stresses that are due to the motion. Think of radiation pressure from photons. That has nothing to do with the internal structure of a photon. That's happening because a photon is pelting your solar sail, for instance. Or if you have a hurricane in South Florida, the dynamic pressure of the wind is blowing your trees. Dynamic pressure actually is a jargon term that's used in fluid dynamics. So you want to separate out the dynamic pressures as well as anything depending on the barycentric flux to get a piece of this expectation value that is just internal stress smeared out by the barycentric probability distribution. Now, this actually also allows us to get things like the internal mass density, momentum density, and so on. So I'm going to look at those first to help build a little bit of intuition and prepare for what's to come. So the mass density, first of all, is given by a 3D Fourier transform. This here I'm writing as effectively a 3x3 matrix. You have initial and final Deuteron spin indices. These can be +1, 0, or -1. And for an actual Deuteron in an actual state, you'd want to sandwich it between some vector and the same vector and spin space on both sides. But this will depend on a Fourier transform of the AU and AT form factors. Numerically, the easiest way to deal with this is to just note that you have particular angular dependency. Wow, I can't speak today. Particular angular dependences in these coefficients. If you do an expansion of this exponential as a sum of spherical harmonics, only one term will survive in each, and you can write your density as a sum of two terms, each of which is given by a one-dimensional Bessel transform with different spherical Bessel functions, 0 and 2. So you have an unpolarized like density and a tensor polarized like density. And for, say, your magnetic number 1 or 0 states, it's a sum of these unpolarized and tensor polarized structures. And if you look at this numerically in terms of plots, this is what you get. Your magnetic number 0 state has the famous donut-like structure, not a sharply defined donut, but kind of a blurry one because the nucleons have finite size and that's being accounted for. So it kind of blurs out the donut. And your MJ plus or minus is kind of like two hemispheres or a very short dumbbell. What's also interesting to look at, besides just the shapes, which are well known, is how they come about in the first place. You can look at the contributions of the S wave, D wave, and interference between both individually. The S wave by itself, of course, it doesn't know anything about direction. It's an S wave. It actually doesn't look quite like a solid ball, but kind of like a caramel truffle, where it has a thick outer shell and is a bit thinner and gooier on the inside. The D wave, interestingly, has the opposite shape of the resulting distribution. You have the dumbbell-like shape in the MJ equals 0, a donut-like shape in the MJ equals plus or minus 1, but the D wave, pure D wave, is very small. Much more significant to the shape you get is the interference. The interference term basically, say in the MJ equals 1 state, gets rid of the poles in your caramel truffle and reinforces the equator. And that's how you get the donut. And similarly for MJ equals 1, it reinforces the poles and subtracts out the equator, which is how you get the kind of short dumbbell shape. There's a reason I'm going into this, and it will help make some of the densities that come next a little clearer. Next, the momentum and mass flux densities. If you were to consider the symmetric energy momentum tensor, these would be the same. But for the asymmetric one, they're different, depending on, in the momentum density case, minus the S form factor, and in the mass flux density plus the S form factor. The reason behind this is that when you use the asymmetric EMT, you are considering the quark spin to carry mass flux. So there's some sort of mass or energy that's spinning around, but you don't consider this flux to carry momentum. It's a bit of a peculiar thing. If you don't like it, you can use the symmetric EMT as well. The symmetric and asymmetric EMTs are both valid, but I'm looking at the asymmetric EMT here. And because of this, the mass flux density and momentum density are different. In fact, because you have mass flux being carried by the quark spins, that doesn't count towards momentum. Your mass flux density is larger than your momentum density. Now here, this is for the MJ equals 1 case, and it's shaped like a donut, which seems to contradict the dumbbell-like shape of the MJ equals 1 mass density, but the mass flux and momentum are concentrated in the D wave, and the D wave contribution to MJ equals 1 is a donut shape. The S wave does not contribute to this. So depending on what quantity you look at the distribution of, you can see a different shape. That's something that's important to bear in mind when you're looking at hadronic structure. Finally, there is the stress tensor. The stress tensor is a pretty complicated object, but there are a few tricks you can use to simplify it and try to understand it a bit deeper. Instead of looking at all 9 of these components individually, first, you can transform to spherical coordinates. If you're looking at the proton and you look at spherical coordinates, you would actually find already a diagonal stress tensor. You would have a radial pressure, and your theta and phi pressure equal to each other and would be a tangential pressure. You can look at the works of Polyakov and Schweitzer, for instance, and they'll talk about these eigenvalues of the stress tensor in spherical coordinates. For the Deuteron, it's a little bit more complicated. You do have these 3 diagonal components, but you have 2 off-diagonal components in the r theta plane. And each of these are not the same. There's a symmetric part and an anti-symmetric part. Now, the off-diagonal components are usually considered to be shear stresses, and it's helpful to consider what a shear stress does. It's effectively a stress arising from, say, you have a cube, a small infinitesimal cube of material, and you have forces acting obliquely on the surface of the cube, so that there's a projection into the cube and a projection along the cube's surface. And what this will do is it will cause the cube to shear, hence why this component is called a shear stress. However, you can always just rotate your cube, and then you no longer have shear. At least for the symmetric part of the stress tensor, you can do that. In fact, for any symmetric 3x3 matrix, you can always diagonalize it by a local rotation. And when you do this, the axes you get are considered to be the principal axes of the stress tensor, and the components you get are called the principal stresses. This is a pretty common thing in classical continuum mechanics. So rather than looking at spherical coordinates or Cartesian coordinates, we always go to the frame in which the symmetric part of the stress tensor is diagonalized to get the principal stresses. We end up getting a stress that at very large distances looks radial, and another that at very large distances looks like it's along the theta direction. So we call that isoradial, so it's radial-like, isopolar, so it's polar-like. They actually follow the shape of the Deuteron. So a donut shape for MJ equals 1, a kind of dumbbell or 2 hemisphere shape for MJ equals 2. And qualitatively, they follow the properties you would expect of a radial or tangential pressure. In the isoradial case, you have a strictly compressive pressure. Whereas in the isopolar case, you have something that's compressive, more where the mass of the deuteron is concentrated, but at very large distances, flip sign becomes negative and is tensile. That's very similar to what you see in the proton, and it's kind of like, just like in the proton, a very diffuse surface tension. Very diffuse because the proton and the deuteron don't have a sharply defined surface like a drop of water does. And without the arrows here, because I don't know how to do the arrows in a clean way on a 3D plot, just magnitudes. These are what the isoradial, isopolar, and azimuthal, because azimuthal is already diagonalized, pressures look like. Compressive for isoradial, tensile further out for the two tangential pressures, as you would expect for diffuse surface tension, and the shapes follow the mass density of the deuteron. Finally, there's the issue of the antisymmetric part of the stress tensor. An antisymmetric matrix cannot be diagonalized by rotation. So these are kind of irreducible shears. They're shears that are there no matter what coordinate system you look at. Interestingly, not only are they non-normal, they're circulating. So if you were to create a little circle of material element or sphere of material element, they would circle around it, which is precisely why you can't eliminate them by rotation. You have vertical circulation no matter how you rotate this. It's also related to the spins of fermions, because the antisymmetric part of the energy momentum tensor strictly comes from fermion spin. The interpretation of what this means is that it's a torsional tension, torsion because it's tension due to turning something, like you might try to turn a screw in a wrench, or you might try to turn the handlebars of a motorcycle. It's caused strictly by reorientation of the quark spins. The rationale behind this is that if you have a quark that's, say, spin up along some axis, if you want to flip it to spin down, your Hilbert space of spin states is a Bloch sphere. You can't flip through the middle of it, you have to go around the sphere. And state evolution in quantum mechanics, except for possibly measurement, if you believe in the Copenhagen interpretation, for instance. But when you're not measuring something, state evolution is continuous. You have to turn the spin to spin down. And this torsion stress is telling you about the stress that's causing the spin direction to move around the Bloch sphere. As evidence for it, we can map out the torsion stress, and in the MJ equals 0 and MJ equals 1 states, they look like this. It's kind of peculiar looking. It looks like two different donuts above each other. But where this stuff is concentrated is precisely at the boundary of the D wave, or at the point where the SD wave interference goes from positive to negative. So what's occurring here is that if you, say, have an MJ equals 1 state, if you're in the S wave, the MJ is carried entirely by the spins of the two nucleons, so they're pointing up. If you go into the D wave, you have ML equals 2, so MS has to equal -1, so your nucleons have to be flipped. So your torsion stress is basically telling you about how, when you go from the S to the D wave, how the stress is reorienting the nucleon spin. Finally, I only have one slide for this. There's the force distributions. You get these from the C-bar-like form factors. You take the divergence of the expectation value of your one-body stress tensor, and you get the force inside of the nucleon. This is very interesting to look at because your forces are non-radial. This happens because you have a tensor force in the deuteron and you have spin-orbit coupling. But if you map out how the force distribution looks in an MJ equals 0 or MJ equals 1 state, you have short distance repulsion away from the center, you have long distance attraction, and somewhere in between, the forces are predominantly non-radial, and they tend to point towards where the mass ends up being the most concentrated, say towards the donut and at the MJ equals 0, or towards the poles in the MJ equals 1. Something to bear in mind with this is that the nucleon has a finite size, and these forces are distributed over the bulk of the nucleus. So this isn't a profile of the nuclear force as it would act on a point like nucleon. This is also distributed over the entire cloud of the Deuteron wave function. So this isn't a force law. It's an average force density. Okay, so wrapping up what I've about, the Deuteron has a very rich stress tensor with lots of stuff going on because it's a spin one system. It has non-radial forces and an intrinsic torsion stress if you use the asymmetric energy momentum tensor. The nucleons are an open subsystem, so the C-bar-like or so-called non-conserved form factors don't vanish if you only calculate the nucleon contributions. If you were to include all of the stresses in the forces themselves due to pion exchange, due to, say, sigma exchange, due to short distance contact repulsion, or whatever other forces are present, if you account for every stress in every part of the interaction as well, the C-bar-like form factors you get from that should cancel the C-bar-like form factors from the impulse approximation, and they should be 0 overall. However, it's very interesting to look at subcomponents so you can study the forces acting on them. There's a lot of future work to be done. Since this is a non-relativistic framework, mass and energy are different, so we could get the energy density, energy flux densities next. We could actually look at separate quark and gluon contributions. That would be interesting to look at too. And the inclusion of exchange currents is a pretty important one. Understanding how the C-bar-like form factors vanish once you account for everything in the system is pretty important. Anyway, hopefully I'm under time. For once I actually am. Thank you all for your time.
Great, any questions, Jim?
Thank you for a very nice talk. If you looked at something like a row, something that is localized, for want of a better word, is there immediately a simplification that happens in all these form factors? A smoking gun for the fact that you don't have two centers, but rather you've got something that's localized. An object that is localized about some position.
So something that's not a donut shape, but
Yes. Yes, I remember many years ago there was interest in this, is it B1 structure function?
oh yeah, there was.
Yeah, is there any connection between the B1, the non-zero B1 structure? If I remember correctly, it was supposed to be indicative of non-point-like behavior, right, of the Deuteron?
So the B1 actually is non-zero even in a pretty standard description, but it's very small. The measurements that came from, why am I forgetting the name of this experiment? I've
It
given
was at the lab, right? There was under the lab.
Well, the experimental measurements were much bigger than any convolution picture. And what this seemed to indicate, if you took them at face value, was that there's some non-nucleonic component or some massive modification to the partonic structure of nucleons in order to account for it. There are caveats that are attached to that measurement, though, which is that they were at very small q squared, so they weren't really in the scaling limit, and the extractions might be contaminated by higher twist effects. So we don't know that. Ideally, the B1 measurement should be redone at much larger q squared with higher twist components better accounted for, or higher twist contributions better accounted for. But that is really a separate thing from the donut-like shape. Like the B1 should be really small, even accounting for the fact that the Deuteron is shaped like a donut.
But there isn't a smoking gun in terms of, I mean, there must be a huge simplification if you have something that is like a row or J psi, or is that not?
I'm not really sure that there would be simplifications. I think that if you were to get something that wasn't so donut shape, that would basically require that the quadrupole moment be very small. So See if I can go back to this. So this AT form factor would probably be one of the more helpful things to look at. If you take the forward limit of AT and you end up getting something very small, then you get something that isn't so dumbbell or donut-like shape. That's more spherical. I think that happens to be the case for the Rho Meson, but I'm not 100% sure on that. I should know because Ian, Chloe, and I did a calculation, but I'm pretty sure the quadrupole moment is much smaller in the Rho. I think it even has the opposite side. Not 100% sure on that, would have to double check.
Yeah, very interesting, the Deuteron case. I have two questions, actually. The first one is related to the pressure and shear forces, like the von Laue condition in the proton or the stability condition, because we have more form factors here.
Yeah,
Are there easy, well, not easy, but, kind of straightforward, relations, the stability conditions that we can see here?
stability conditions. I'm a little bit skeptical of some of the stability conditions, to be sure. The von Laue stability condition does translate in a pretty straightforward way. Basically that the integral of the pressure has to be zero. That's mathematically trivially satisfied if all the C-bar form factors vanish, which they should if you account for everything in the system. For the negativity condition for D of zero, that if you were to take it at face value, I think that it would imply that certain linear combinations of some of the D-like form factors have to be negative at zero momentum transfer. But some of them will be weighted by deltas. So I think it would ultimately amount to this du form factor having to go to a negative value, which it does for all of the calculations. There is an interesting caveat. Unfortunately, I didn't include the plot in this. If you assume the nucleons are point-like, this form factor is small and slightly positive. But does that actually violate the negativity condition? The nuclear force accounts for the finite size of the nucleon in it. So it might be inconsistent to use point-like form factors and a nuclear force that has finite size effects. Maybe there would be no such thing as a stable deuteron if the nucleons were point-like. I don't know. It doesn't feel entirely straightforward, but in nature, du of zero looks like it's very negative.
Yeah, as a second question, maybe, for the angular momentum condition, because now we have many form factors again, and the unsymmetric part is really, I guess, related to the intrinsic spin contribution and the orbital one,
Yeah.
the symmetric part. So because you have many form factors now, maybe to check like how much come from the intrinsic spin and how much come from the orbital angular momentum to the total angular momentum of the Deuteron?
Oh, we have formulas for that, but I didn't do the numerics. I'll have to check that and get back to you. We should probably add it to our paper, actually. It of course depends on what you assume for the spin contribution to the proton, which we're using the JAM22 results for our numerics for SN, but we should be able to get a number for that. And actually, we should add it to the paper. That's a great suggestion. I think it's slightly smaller than for the proton because you have this deuteron depolarization factor. We'll have to check though. Yes.
Yes, so why did you choose to use a different wave function for the deuteron than previous works on the subject?
Well, one of the previous works was ours and we used the same as our previous one. And these two both use different than each other. The reason I use AV18 is because I have the code for it. I know Bob Moringa pretty well, and I trust AV18 to be accurate. Oh, wait, you had a question first.
So just thinking about potentially measuring something, the introduction of tensor polarization really gives a lot of extra form factors.
Yes.
And so how would you go about accessing them?
Yeah, that's actually a really good question. It's the thing that I didn't talk about all in the talk because it's not something I feel like I can give a really informed and accurate answer on necessarily. So there are only a limited number of ways that people know how to measure these EMT form factors currently. One of them is to try to extract generalized parton distributions. So you need to look at these ST-HEP processes like deeply virtual Compton scattering or other 3-2 processes that might be more sensitive to the X dependence. And then you need to take a Mellon moment of your GPDs. There's also the work done by Yoshitaka Hata and collaborators at looking at near threshold meson production as a way of accessing the EMT form factors for the proton. It would be interesting if it were possible to look at this on the Deuteron too. I don't know that anyone's looked into this, so I don't know whether it is possible. And then if it is possible, it's a matter of, can you prepare a tensor polarized target and do this experiment?
That near threshold mesons is it a high Q-squared measurement?
I don't know enough about it to confidently answer. I feel like it would have to be, but I don't know for sure. That's why I didn't include any slides about it. I don't actually know the topic that well. You had a question first and then you.
Are there conditions under which you would expect for relativistic effects to become relevant?
That's a good question too, and I don't know offhand. There is a way I was thinking about of trying to estimate error due to using a non-relativistic framework, and that actually goes back to this breakdown in the first place. So here I have space-like indices. If you were to put time-like indices too, in the relativistic case, you'll basically get the same breakdown. But in the non-relativistic case, the Galilei symmetry is less constraining than the Lorentz symmetry. So for T00, T0I, you would get new form factors. The new form factors in nature should be zero because nature is Lorentz invariant. If you do this calculation in a non-relativistic framework, and you get non-zero values for these additional form factors, that could be an estimate of how wrong you are for using non-relativistic quantum mechanics. I don't know what to expect, but I feel like the Deuteron is pretty well understood when you're looking at just its static structure to be reasonably well described as a non-relativistic system, though you do need to account for relativistic effects if you're looking at processes in which you have, say, high momentum knockout. So I'm not really sure, but that is an idea for how to estimate it.
I have a general question. So if you are going to compute this on lattice, let's say this form factors, what kind of, would you use one local operator for the Deuteron or you'd use two separate local operators for each constituent nucleons?
I have no idea.
Is there any calculation on the lattice?
I would have thought the former, right? You just have one operator then
Yeah, I'm not sure.
measuring.
Some people have done Deuteron calculations. I guess if you just have one operator with the quantum numbers of the Deuteron, it technically would account for all the interactions. So it would be a complete calculation instead of the impulse approximation calculation.
If you use, let's say, one local operator just to create this Deuteron state, then it would be very similar to, let's say, for spin one meson.
Yeah.
Form factors. Then this form everything you are saying is going to translate to the spin one mesons. You have the same answers for the EMT.
So
the spin one.
a lot of what I say translates to the mesons. There's a small number of things that I've done that depend on the framework being non-relativistic. One of them is precisely this idea that, say, if you take an unpolarized ensemble, only this term survives. Now, if you have a relativistic formula instead, these epsilon vectors are not actually invariant under boosts. 3-component vectors, they're invariant under Galilei boosts. So this is the same in every frame. But the epsilon vectors are in relativity are no longer boost invariant. And if you were to say, take epsilon prime at different momenta, contract them with each other, do an unpolarized average, you no longer get 1 or -1, you get some order delta squared over m squared correction. So you're going to get a mixture of different form factors for the unpolarized mixture. So some of the interpretation of these things as being unpolarized or tensor polarized, that depended on being non-relativistic. But the same structures, Lorentz covariant forms of these same structures will all appear in the relativistic case. It's the same 11 form factors, same 9 if you drop the antisymmetric parts. These two works from which we kind of borrow but then modify the breakdown are Lorentz covariant relativistic frameworks. Kosin et al. Has the 11 for the antisymmetric, for the asymmetric. Polyakov and Sun have the 9 for the symmetric. So a lot of the stuff translates, and Polyakov and Sun's paper does an excellent job talking about things like the monopole versus quadrupole structure in a relativistic context. So it mostly translates, but there are some caveats about interpreting polarization ensembles.
Any more questions? Looks like Adam again.
Thank you for your time.